So how do modern AI applications save their data? ChatGPT is able to remember all the past conversations, while GitHub Copilot is able to scan the code repository and then make references to it. Well, all of that data is stored in a type of a database called a vector database. Now, I expect this video to be quite informative and interesting, so if you've never worked with vector databases, or you simply want to learn more about that topic, stick around because this is going to be the video for you. Now we're going to start with some theory and then jump into the practical part slowly. So let's take a look at this example. We have a RAG pipeline, so Retrieval-Augmented Generation, which is finally spitting some text out. Let's say we're basically ChatGPT, right? So we're going to get some user prompt, and the Planner LLM, that's the first service or LLM that parses the user's prompt. It's kind of an orchestrator, and it has to decide whether it retrieves an extra context or extra data from somewhere, like our vector database, or maybe it scrapes the web. And it does it based on the user's prompt and its clues. For example, in this user prompt, we say, keep in mind. So it's kind of a clue that the Planner LLM notices, and it says, oh, it seems like I need to save something in my database or retrieve something from the history, because something tells me that keeping in mind sounds like saving in a memory. So it decides, instead of going directly to the reasoner LLM for it to give an answer right away, it decides that, hey, I actually need to retrieve something from my memory or save something in my memory in this case. And the memory happens to be our MongoDB, which is a vector database. So after it can retrieve the data, it does it and passes this data to a reasoner LLM. Reasoner LLM now has this context that it got from a MongoDB, a vector database, and it has its own knowledge here. So it packages it together and then spits the output, sends it back to the user. Now, this is one of the use cases where a vector database can be used, so a RAG pipeline. But you can also use it for simple semantic product search, like literally text search, which is semantically similar. Some duplicate detection or personalized recommendations, right? Now, I want you to understand that a vector database is very different from a normal databases that everyone is used to. How? Let's take a look at MongoDB's vector search. So MongoDB has Atlas. MongoDB Atlas is a cloud-based managed service provided by MongoDB that doesn't only take care of the flexibility, scalability, security, and backups, but it also has a built-in native support for vector search. And this is exactly what we need. Meaning, we kind of eliminate the need for us to have a separate vector database, because our main database and the vector database can be just one MongoDB database. And as you can see in this query, we can retrieve the metadata for our business need, as well as the embedding for our AI feature, just in one single query. How crazy is that? And also, there are a lot of misconceptions about MongoDB. MongoDB is actually fully ACID compliant. MongoDB is not only eventually consistent, but it's fully consistent. And also, it has a capability for transactions. Yeah, you can have transactions across different collections, as well as different shards. So just keep this in mind. MongoDB is a great solution, and MongoDB Atlas has a free tier that I'm currently using to demonstrate this video. So basically check it out. And once again, thanks to MongoDB. So I already have my database here that I'm going to demonstrate in a minute, but let's go over some theory for one more minute. So a vector database is basically going to look like this. As you saw, the embeddings are arrays with numbers between 0 and 1. So a dog would result in this kind of an embedding, and a puppy would result in this, and a car in this. Do you see any interesting similarities here? You can notice that the dog is actually, the values of the dog are not that far from the values of the puppy. So 0.1 is almost like 0.09, whereas car is way further than all of these values. Meaning, semantically, it has a completely different meaning. Now, how are these values mapped into these vectors or arrays? Now, it's done with the help of an embedding model. An embedding model is a neural network that accepts some corpuses of text and then spits out embeddings for either sentences or words. And they are pre-trained models that big companies like Hugging Face or OpenAI are able to provide. For example, text embedding 3 small, or Hugging Face has this A11 mini LM embedding that everyone can pretty much use. Now, in a space, in a 2D space or a 3D space, actually there are more spaces, dog and a puppy will be very close to each other, while let's say this one is a car. As you can see, it's very far from the dog and a puppy because it's neither a dog nor an animal. Now, how do we make all of the data end up within our vector database? So here I have my IT support database, which is basically one collection called IT support tickets, and it's the common tickets that come up that people are asking for. For example, email attachments blocked, or cannot connect to VPN from home. And these are plain JavaScript objects. The interesting thing here is that we have this property called embeddings, and this is a huge array. Meaning we embedded this title here or some semantic value for this ticket in an array. And later we would need to search for the embedding of this ticket to retrieve similar tickets, all right? So let's answer the question, how does this corpus of text, for example, from the MongoDB documents end up within such a database? Well, first of all is chunking, right? We're gonna chunk this huge document into sentences. So let's say one sentence is 2 different chunks, and then these chunks are passed through an embedding model. For example, text embedding 3 small that we saw before. And since this can accept a text and spit out an embedding, we're going to give these 3 different sentences and we're going to retrieve 3 different embeddings. And this is something we're going to eventually save in our database. As you can see, all of my entries have embeddings and they have the same number of entries inside. All right. Now, these embeddings are stored in the database. Okay. Now, when the user makes a prompt, let's say how to restart my specific version of Docker, we don't only want to search for a relatable or related answer within our catalog, but we want to extract the semantic meaning from our sentence, which is going to be our embeddings, so our vector, and then compare this vector to everything else that we have in the database. And the way we compare those vectors is done with an algorithm called approximate nearest neighbors. And a subset of it is called HNSW, hierarchical navigable small world graph. This is an interesting algorithm, and I'm gonna leave the description for you to go over it because otherwise this is gonna take a long time. But it's very interesting how it works, and it uses an Euclidean distance to finally find similar embeddings. And let's say we go to our MongoDB Compass, and I already created one pipeline here, or aggregation pipeline. Let's say it consists of 3 stages. And in the first stage, I'm simply going to look for some semantic meaning. So this is my query vector, and this is some kind of a sentence that I'm looking for, right? So semantic sentence is going to give me some tasks or tickets that are already similar to my query vector. Then the query vector is going to be filtered by priority high. So only tickets that have priority high here is going to end up in my list. And the stage 3, I simply want the title of these tickets. So I give a project or a projection stage, and this is my final data here. This is pretty much how the semantic search is going to work within MongoDB. And as you saw, this is pretty simple to use and easy to understand. If you still have any questions, guys, let me know down below in the comments. I'm gonna try to answer them. Hope you learned something new. Smash like and subscribe, and check out MongoDB in the description below. I'll see you guys in the next video. Goodbye.